Okay, moving into the first law of thermodynamics here. The first idea related to the law of thermodynamics is that similar to the law of conservation of mass or matter, is the same idea in regards to energy. So energy isn't created or destroyed, it's simply kind of exchanged or moved around. So the total energy of the universe is a constant, meaning that a system might lose energy, but it's going to move. It is then gained by the surroundings, and that kind of plays off of our earlier discussion regarding the system versus the surrounding. You can kind of look at the graphics in regards to that, but you can think of if you have a starting reaction, if it gives off heat, if it's exothermic, then it's giving off energy to the surroundings and yeah. Okay, one idea of when we talk about a system, so the internal energy of a system is the sum of all the kinetic and potential energies of all components of the system, and we call this E, and this will eventually work at deriving some stuff to look at how energy kind of moves through the system. But in chemistry, we often are calculating the potential energy, and then kinetic energy might come into play when we measure the temperature of the system or the temperature of that's occurring during the reaction. And the change in internal energy, or delta E, is the final energy of the system minus the initial energy of the system. And we will utilize delta E more than we will actually utilize the E final and E initial. Okay, so idea being here is when we have hydrogen gas and oxygen gas, they combine to form water. Well, so remember, delta E is the change in energy of the system. So if it's greater than 0, or it's a positive value, so that is, it takes energy to separate water to move it into separate hydrogen gas and oxygen gas. So technically we have to add energy into the system, so the internal energy increases to split water. And then so energy change, so this type of energy change would be called endergonic, and this is where we eventually get led to endothermic, but we'll get there in a sec. Okay, the opposite is when you combine chemicals together, or in this case, the energy given off to the surroundings increases, and therefore the internal energy of the system decreases. And this is the idea of an exergonic, and this leads us to, hopefully you're kind of getting the theme, but this is going to lead us to exothermic type reactions. So when energy is exchanged between the system and the surroundings, it is exchanged as either heat or work. So heat being obviously the movement of heat, but then work is like it expanded a piston or something was done. So two ways that we can measure the behavior of a reaction. We can then have an equation, a relationship of the heat and work of the system is equal to the change in energy of the system. So thinking through kind of the behavior. So so for Q, so again, Q stands for heat. So if Q increases, this means the system gains heat. So heat is being put into the system, or the system absorbs heat. If Q is negative, this means the system loses heat, or heat goes to the surroundings. And then for W, for work, this means work is done on the system. And then if W is negative, it means work is done by the system on the surroundings. And then for delta E, if delta E is positive, this means there's a net gain of energy by the system. So the overall system has absorbed energy. And then if it's negative, delta E is negative, then that means there's a net loss of energy, or more energy has gone out into the surroundings versus to the system. So when heat is absorbed by the system from the surroundings, this process is called endothermic. So thermic, heat energy. Okay, so you've heard that word, but that's when heat is absorbed by the system. Exothermic is the opposite, when heat is released by the system into the surroundings. We call that exothermic. All right, let's talk about a state. So usually we don't necessarily have a way of knowing the internal energy of a system at one given point. Like we can't say, oh, at this given point, this solution has this internal energy. So it's usually too complicated to figure out. But what we can do is measure the change in a system. So it doesn't necessarily, so the idea being, we do know that the internal energy of a system is independent of the pathway which the system achieved that state. So let's say you have this beaker in the middle, 50 grams of water at 25 degrees Celsius. So the water could have reached that room temperature by either being heated up from 0 degrees Celsius or being cooled down from 100 degrees Celsius or anything in between. So where it is now is independent of how it got there. So internal energy is what we call a state function, meaning it depends only on the present state of the system, but not on the path by which the system arrived at that state. So delta E, or the change in energy of a system, is only dependent on the initial condition and the final condition, like what has changed. Okay, now this is so this is important. So delta E and like the energy of the system, that's a state function, isn't dependent on how it got there. The heat and the work are not state functions. So our example here being, so let's say we have this battery, a charged battery, and then we have a discharged battery. Okay, one way that the battery could become uncharged is by heating, running its power through a heating coil, and all that heat just dissipating into a room or something like that. Okay, and so the path that it took to discharge was by giving off heat. But if let's say you plugged in that battery to a fan, well, you'd have heat given off because you're always going to lose a bit of heat in any electrical process. But then you also, work is done on the surroundings by that fan moving. And so in both instances, you lost the same amount of energy, but the heat and work of that that was done is different. So Q and W are not state functions, not fixed, but the delta E is. Like, it is a state function. It doesn't matter how the heat, whether it was heat or work or a combination, those don't matter. Okay, so work is usually in an open container. The only work done is by a gas pushing on the surroundings, or by the surroundings pushing on the gas. This is in like a closed, open container. Things able to kind of move back and forth. So like a volume change we might look at. So we can measure the work done by the gas if the reaction is done in a vessel that has been fitted with a piston, because then we can measure the change in volume of that piston. Here we have some hydrochloric acid, some solid zinc. We have the zinc fall into the hydrochloric acid. We produce hydrogen gas, and then we move that piston a certain distance. So the work is going to be equal to negative pressure times the change in volume. And that is going to be it for today. I think we'll continue enthalpy on Wednesday. Thanks.